Hello! Today we're starting a new chapter, Chapter 14, which is all about chemical kinetics. So last time we finished Chapter 17, so now we're kind of going backwards in the textbook. So let's start by defining chemical kinetics. Chemical kinetics is the study of the factors that affect the rates of chemical reactions such as temperature. And your textbook goes over an example of what are called ectotherms. So those are animals that regulate their body temperature based on their surrounding temperature, whereas mammals regulate their body temperature through metabolic activity. So down below we have a nice little graph of a lizard's body temperature throughout the day. So in red, we can see that the lizard's body temperature increases. So it's going to increase during the day and decrease at night. So what we can do is measure the rate of the temperature change throughout the day. So initially, the temperature is increasing, and then later on it's decreasing. So we would have an increase or positive rate at the beginning of the day, and then we would have a decrease or negative rate at the end of the day. And this also works with chemicals. So far we've been talking about equilibrium and how chemicals will react with each other to give products. But those products can also react with each other to give us back the reactants until they reach equilibrium. So now we're going to talk a little bit more about the rate of those reactions. And this is particularly important because some chemicals like to react slowly, others react more quickly. And if you try to, let's say, heat up a certain chemical to make it react faster, that could cause the reaction to go haywire, for instance. So we do need to be aware of these chemical rates. But additionally, this is also important in biology. For instance, our bodies have certain metabolic rates that if they go too slow or go too fast, that can have negative consequences. So remember that with rates, we're really talking about the speed. So the speed of a chemical reaction is called its reaction rate. So the rate of a reaction is a measure of how fast the reaction makes products or uses up reactants. And again, the ability to control the speed of a chemical reaction is really important. All right, so let's define rate in a little bit more detail. So rate is how much a quantity changes in a given period of time. For instance, the speed you drive your car is a rate. The distance your car travels, typically in miles, in a given period of time, which is 1 hour. So we record the rate at which our car goes in terms of miles per hour. In other countries, they use kilometers per hour. So we're going to do the same thing with chemicals. Typically, we report rates in terms of concentration over time. All right. So again, the rate of a chemical reaction is generally measured in terms of how much the concentration of a reactant decreases or product concentration increases in a given period of time. All right, so that would kind of look like, for instance, the change in concentration of A over the change in time. Now, for reactants, remember the concentration is going to decrease over time because reactants are being used up. So we're going to place a negative sign in front of the change in reactant concentration, because that's going to symbolize that we're losing reactant concentration. So for the reaction where hydrogen and iodine produce hydroiodide or hydroiodic acid, we're going to see that the rate is equal to the negative of the change in concentration of hydrogen over a change in time. Now, if we break that down a little bit further, we have the negative of the concentration of hydrogen at time 2 minus the concentration of hydrogen at time 1. So we're taking the final minus the initial concentration. And then we're dividing that by time 2 minus time 1. So our final time minus our initial time. Okay. So again, we're just tracking the change in concentration over a change in time. Now there are a couple of other terms. For instance, the average rate is the change in measured concentrations in any particular time period. So down below, we have a table of some time points versus measured concentration of hydrogen. And what we can do is take the difference. So you'll notice here, we're taking the difference in the initial concentration of hydrogen over a second concentration in hydrogen. And then we're also going to divide that by the time difference, which is just 10 seconds, 10 minus 0. So the change in concentration of hydrogen is negative 0.181, and then that's over 10 seconds. So our rate is the negative of the change in concentration over change in time. So our rate would equal 0.0181 molarity per second. So that would be our average rate for that particular time period of 10 seconds. Now we could do the same thing for these other data points. So maybe we continue to take measurements every 10 seconds. We can then take the difference in our second measurement and third measurement, and then divide that by the difference in time, which is again 10 seconds. And our rate would then be 0.0149 molarity per second for that particular time period. And we could keep going. Now, the larger the time interval, the more the average rate is going to deviate from something called the instantaneous rate. So, for instance, if we could also just take the total difference here between the last time point and the first time point and figure out an average rate there. But that's going to deviate significantly from, again, something called the instantaneous rate. So the instantaneous rate is the change in concentration at any one particular time. So for instance, if we wanted to determine the rate at 10 seconds exactly, what we would do is if we had, let's say, a graph of the change in concentration over time, then we're going to determine the instantaneous rate by taking the slope of a line tangent to the curve at that particular point. So this is actually called the first derivative of the function. All right, so again, the instantaneous rate is the rate at a very particular point, whereas the average rate is over a specific time period. So let's look at a graph of the change in concentration for a reactant and the change in concentration for a product. And again, we're looking at the reaction between hydrogen and iodine, which is producing hydroiodic acid. So down below on this graph, it looks a little complex, but we'll step through it. You'll notice that we have concentration on the y-axis, and that's in moles per liter. And then we have time on the x-axis in seconds. And then we're tracking the change in concentration for hydrogen, which is in green. So you'll notice it's decreasing over time. And that makes sense because it's the reactant, so it's going to get used up as time goes on. And then we're also tracking the change in concentration for the product, hydroiodic acid. And you'll notice that that's increasing with time because we're producing more product. Now, if we wanted to determine the instantaneous rate at, let's say, 50 seconds for our reactant, hydrogen, what we do is we draw a line or a tangent line to that point. Of course, I can't draw that very straight, but you get the idea. And then essentially what we're doing here is creating a triangle. So we're going to determine the change in our y-axis and then the change in our x-axis for that line. So if we track the change in y, that's the change in concentration. So for hydrogen, we're losing 0.28 moles per liter. And in terms of time, this is a time period of 40 seconds. So then to calculate the instantaneous rate, we're going to take the negative of negative 0.28 moles per liter and then divide that by 40 seconds. And remember that negative sign in the front is there because we're losing hydrogen as the reaction proceeds. So our instantaneous rate would then be 0.0070 moles per liter per second. And again, this would be at exactly 50 seconds, so that is our instantaneous rate. And then we can do the same thing for the product. So the instantaneous rate would be, again, dependent on a tangent line. And then we're going to track what is the change in concentration versus the change in time. And we should get the same exact result, so 0.007 moles per liter per second. Now you might notice there's this 1/2 here. That's coming from the stoichiometry of the reaction, so we'll talk about that in a second. So again, there is a difference between the average rate and the instantaneous rate, and the average rate can be pretty equivalent to the instantaneous rate, but the time period that you're looking at should be really small in order for that to be true. Now, as time goes on, the rate of a reaction generally slows down because the concentration of the reactants decreases. So you'll notice that these curves are starting to kind of level out as we go on. And again, at some point, we'll reach a time point where the concentrations are no longer changing. So at some time, the reaction stops, either because the reactants run out or because the system has reached equilibrium. All right. So let's talk a little bit more about that reaction stoichiometry that I mentioned. So in most reactions, we've seen that the coefficients for a balanced equation are not all 1 to 1 to 1. For instance, in the reaction of hydrogen and iodine, we have a ratio of 1 to 1 to 2. So for these reactions, the change in the number of molecules of one substance is a multiple of the change in the number of molecules of another. So for instance, in that reaction, for every 1 mole of hydrogen used, 1 mole of iodine will also be used, but then we're producing 2 moles of hydrogen or hydroiodic acid. So the rate of change will be different for each of those different molecules. Because again, we're producing twice as many hydroiodic acid molecules as reactants being used. So in order to be consistent, or in order to obtain the same rate, we're going to use a factor in front of each of our changes in concentration per time. So for a generic reaction where A plus B becomes C plus D, we also have coefficients. So I'll write those in lowercase letters. And if we were to define the rate of a reaction based on just reactant A, we would write negative 1 over A, or 1 over the coefficient, times the change in concentration of A over the change in time. And remember that negative sign is there because we're losing reactant. And then we do the same thing for B, because it's a reactant, but we're going to multiply it by 1 over its coefficient. And then for C and D, because they're products and we're gaining product, those don't have negative signs, they have positive signs. So for C, we would have positive 1 over the coefficient for C times the change in concentration of C over the change in time. And then we'd have a similar expression for D. So, for example, let's write out these rate equalities for the reaction above. So let's define the rate in terms of hydrogen. So that would be negative 1 over 1, because the coefficient is 1, times the change in concentration of hydrogen over the change in time. So we could also just write that as negative delta H2 over delta T. We don't have to include the fraction there because it's just 1. And then we could also define the rate in terms of iodine. So that would also be negative because we're going to lose reactant. And then the coefficient again is 1. And then we'll write delta, oh, if my pen will work, delta concentration of I2 over delta T. And now let's do that for the product. So the rate in terms of the product, and let me just erase my little squiggle mark there. Because this is a product, we're gaining hydroiodic acid, so we're going to have positive 1 over the coefficient, which is 2, and then multiply that by the change in concentration of the product over the change in time. So this would be 1/2 of the rate expression. Now, again, we have to multiply the change in concentration over time of hydroiodic acid by 1/2 because in order for the rate to be equal to the rates of the reactants, we do need that 1/2. Again, remember we have a 1 to 2 ratio, so we have to take that into account in order for all of our rates to be equal for this reaction. Okay, so let's go over an example. We're going to consider the balanced chemical reaction where hydrogen peroxide, H2O2, is reacting with iodide ions and hydrogen ions to produce I3- and water. So in the first 10 seconds of the reaction, the concentration of iodide ions drops from 1 mole per liter to 0.868 moles per liter. So first, we're going to calculate the average rate of this reaction in this time interval. And second, we're going to determine the rate of change in the concentration of hydrogen ions, or change in concentration over time, during this time interval. Okay, so let's start with A, and we're going to calculate the average rate of this reaction in this time interval. So let's write out the rate expression in terms of iodide ions because that was the information we were given. So we're focused on that part of our reaction. All right, so the rate will equal, let's see, we have a reactant, so we have to put a negative sign there. And then the coefficient is 3, so we're going to multiply this rate expression by 1/3. And then it's just the change in concentration of I- over the change in time. Now remember, if we write that out, what we have is the concentration of I- at time 2 minus the concentration of I- at time 1, all over time 2 minus time 1. So let's plug in what we know. So the concentration of I- at time 2 is 0.868 moles per liter. And I'll put parentheses around this. And then we're subtracting the concentration of I- at time 1, and that was just 1.000 moles per liter. And then we're dividing that by time 2, which was 10 seconds, minus time 1, which was 0 seconds. Because it did state that we were in the first 10 seconds, so we'll just take 10 minus 0 there. Okay, so now if we plug that all into our calculator, we should find that the rate is 4.4 times 10 to the negative third moles per liter per second. So that is the rate of our reaction. All right. So now in part B, we're asked to determine the rate of change in the concentration of hydrogen ions. So delta concentration of hydrogen ions over delta time. So we now know that the rate is equal to 4.4 times 10 to the negative third moles per liter per second. And now we want to solve for the change in hydrogen ions over those first 10 seconds. So let's write our rate expression here for H plus. So rate will equal, again, this is a reactant, so this has to be negative. And then we have a coefficient of 2 in front of the hydrogen ions, so we're going to multiply this by 1/2. And then that's delta H plus in brackets over delta T. All right, so now we're going to plug in the rate that we just calculated for this reaction into our new expression, and then we'll solve for delta H plus over delta T. All right, so let's write that out. Okay, so in order to isolate this expression that we're trying to solve for, we're going to multiply both sides by -2, because that will cancel out our -1/2. Okay, and then I'll use a different color since I'm kind of running out of room here. So if we multiply the rate 4.4 times 10 to the -3 by -2, that will give us the change in concentration of hydrogen ions over the first 10 seconds of the reaction. So delta H plus over delta T, that should equal, let's see, -8.8 times 10 to the -3 moles per liter per second. And I apologize, I ran out of room there. Okay, so we're going to lose 8.8 times 10 to the -3 moles per liter for every second within that first 10 seconds of the reaction. Okay. So hopefully that helped to see how we set up these rate expressions and how we can utilize the stoichiometry to figure out what is the rate for this reaction, but also what is the change in concentration for a particular reactant over a particular time interval. Okay, so now let's work on a worksheet problem. So this is worksheet problem 1, and I did post the worksheet for chapter 14. So if you want to download that, you can, or you can just follow along with the PowerPoint slides. And we're going to consider the reaction where 2N2O decomposes into 2N2 and O2. So we have nitrous oxide, and it's decomposing into nitrogen and oxygen. So in A, we're going to express the rate of the reaction in terms of the change in concentration of each of the reactants and products. So we're just going to write out those rate expressions. And then in B, in the first 15 seconds of the reaction, 0.015 moles of oxygen is produced in a reaction vessel with a volume of 0.5 liters. What is the average rate of the reaction during this time interval? So this will be pretty similar to our previous example problem, but we're just going to have to calculate the concentration based on the number of moles and the volume. And then in C, predict the rate of change in the concentration of N2O during this time interval. All right, so let's start with A. And again, we're asked to Express the rate of the reaction in terms of the change in concentration of each of the reactants and products. And again, if you want to try this on your own, you can always pause the video. All right, so let's start with our reactant, N2O. And again, for reactants, because we're losing the reactant, we're going to put a negative sign in front. And then the coefficient here is 2, so we're going to multiply this by 1/2. And then we're just writing out the change in concentration of N2O over the change in time. Now this will also be equal to any addition of product. So let's start with nitrogen. Again, because this is a product, we're gaining some amount. So we put a positive sign. And the coefficient in front of nitrogen is 2, so we're going to multiply this by 1/2. And again, that's just to set it equal to the rate of the overall reaction. And then we'll just multiply that by the change in concentration of N2 over the change in time. And now this is also equal to positive, because for oxygen we're gaining oxygen, and the coefficient's just 1, so I'm going to leave out that 1/1, and it's just the change in concentration of O2 over the change in time. Okay, so now we have our rate of the reaction in terms of each of the reactants and products. So now we can use this information for part B. In the first 15 seconds of the reaction, 0.015 moles of oxygen is produced in a reaction vessel with a volume of 0.5 liters. What is the average rate of the reaction during this time interval? So we already said that the rate is equal to the positive change in the concentration of O2 over the change in time. So that was from our previous slide there. So now we can just plug in what we were told. So let's calculate the concentration of O2 after the first 15 seconds of the reaction. All right, so that's our concentration at time 2. And we would just subtract 0 moles per liter for time 1. And then we're going to divide that by time 2, which is 15 seconds, and subtract by time 1, which is 0. All right, so the concentration of oxygen at time 2 should come out to be 0.030 moles per liter. And again, we're just subtracting the concentration at time 1, which we're assuming was 0. And on the denominator, we'll just keep that 15 seconds minus 0 seconds. All right, so if we plug that into our calculator, we should find that the rate of the reaction, or the average rate of the reaction, is 0.002 moles per liter per second. Awesome. So for part C, we're asked to predict the rate of change in the concentration of N2O, so our reactant, during this same time interval. Okay, so in other words, what is the change in concentration of N2O over the change in time? So remember from our first slide here for this problem, we had this expression for the rate for N2O. So let's use that same expression here. And we already said that the rate from the previous slide is 0.002 moles per liter per second. So now what we want to solve for is just the change in concentration over time for N2O. All right, so what we'll probably do is multiply both sides by -2 so that it cancels. And we're just left with the change in concentration over time. So if we multiply the rate by -2, we should find that the change in concentration of N2O per time is -0.0040 moles per liter per second. So we're losing on average 0.004 moles per liter of N2O for every second within those first 15 seconds of the reaction. Now again, that rate might change in other time periods because remember, as a reaction goes on, the change in concentration can level out until we hit a change of 0. So we might find that in the next 15 seconds of the reaction, the change in concentration is lower because we're starting to run out of the reactant, for instance. All right, so now let's also work on problem 2 of the worksheet, just to get in some extra practice here, because this is a lot of new stuff that we're covering. So let's consider the reaction where we have 8 H2S plus 4 O2, and that's combining to produce 8 H2O and S8. And we want to complete the table below. So we're already given that the change in concentration of H2S over time is -0.08 moles per liter per second. And then we want to find the change in concentration of the other reactant and the two products. And then we also want to find what the rate of this equation is. So there's a few different ways that you could solve for this problem. So let's just write out the expressions for everything. So for H2S, that is a reactant, so it's negative. And then the coefficient is 8, so we're multiplying by 1/8. And then it's just the change in concentration over time. And then for our other reactant, oxygen, that would also be negative, and the coefficient is 4. And then it's just the change in concentration over time. And then for our products, we have positive 1/8 times the change in concentration of water over time. And then we have positive 1/1, since the coefficient is 1, times the change in concentration of S8 over time. So we already know what delta H2S over delta T is. So we could use any of these relationships to solve for what we don't know. So for instance, maybe what we'll do first is solve for the rate, and then we can use the rate to solve for the other three components of this reaction. Or you could start just by solving for, let's say, let's say you isolate this equality. You could solve for the change in oxygen over time. And then you could do a similar thing for the products. It's really up to you. What I'm going to do, though, is solve for the rate first, because that just makes sense to me personally. but you could do it a million other ways. All right, so I'm going to start again by solving for the rate. So we said that the rate was equal to 1/8 of the change in H2S over time. So I'm just going to plug in that value for delta H2S over delta T, which was negative 0.080 moles per liter per second. So because we have two negatives here, that should give us a positive answer. And then 0.08 divided by 8 gives us 0.01 moles per liter per second. So that will be our rate of the reaction, or the average rate. All right, so now we can use that information to fill in the rest of the table. Okay, so let's solve for oxygen. And here I'll just rewrite what we just solved for here. So now that we know that the rate is equal to 0.01 moles per liter per second, I'm going to set that equal to negative 1/4 delta O2 over delta T. And now we can solve for delta O2 over delta T. So we're probably going to multiply both sides by -4. Oh, wrote that backwards. So we'll multiply both sides, and that will give us, let's see, negative 0.04 moles per liter per second for the change in concentration of oxygen over time. So now we can plug that value in for oxygen. So now I'd like you to try to solve for the other two boxes. So try to solve for the change in concentration of H2O over time, and also try to solve for the change in S8 over time. And of course, I'll post the worksheet keys so that you can double check your answers later. All right, so next time we'll start talking about how to actually figure out the rate of a reaction using different instrumentation. So I'll see you there.